Alright, recording. We are good to go. Alright, well, I would like to go through ODP 205, which I just posted, and I also posted PA2. So we're going to talk about those, and then we'll start developing more details on some of the algorithms that we're going to use for linked lists implemented in dynamic memory, so PA2. Let's start with the ODP. Alright, so ODP 205, you're writing some code to work with this new type of struct node that we're using in the next programming assignment. So this is a node comprised of two fields, not three. The first one is still an integer, which is a data value. The second one is a genuine pointer to a struct node. There's no valid field here because we're not managing the allocation and freeing of these blocks of memory that turn into nodes. That's being managed by the system. We allocate by calling malloc, we release by calling free. So that takes care of the valid bit. So our node structure is simplified, a data field and a next field. So the nodes, in some sense, look much more like these pictures that you keep seeing me draw, where we have a data field and a pointer and a data field and a pointer and so on. Alright, so you're creating a function named set. And what is the goal of set? Set takes a pointer to a struct node and it adjusts the values of that node's fields. In particular, it takes the data field and it doubles it, so multiply it by 2. And it takes the next field and sets it equal to null. So if I have a node, let's say it's called test, and it's got a 15 and it's got some next field, and I were to call my set function with a pointer to this node, what the set function is going to do is change this to a 30 and change this to null. And that's all it does. It's not necessarily something that you're going to use in PA2, but it's a similar set of operations. So set is a function. We pass it a pointer to a node. It looks at the data value, multiplies by 2, stores that back in the data value, and it sets the next field equal to null. And that's it. So there's the function prototype, right? Pointer to a struct node is the argument, doesn't return anything. The test bed that I've made for you is under /temp ODP 205.0. So implement your function, test it, and we'll talk about ways to test it in a moment, and then when you're all set, go ahead and link it with the official test bed and then assess it. All right, so how do we test this on our own? So let's say this is my test main program. So set up your struct node. Right, and then in your main program, make yourself a struct node. Doesn't matter what you call it. I'll just call it haha. And let's set up some fields. Let's set the data value to 11. And let's set the next field equal to 1999. I'll get some compile warnings when I do this because this is a pointer and this is an integer. But that's okay. I'm just trying to give it some value other than null. Right? So let's do some prints. Print haha.data and haha.next. And make sure that you know what those values are. And then call your set function. And since haha is not a pointer to a struct node, but it's actually a struct node, I'm going to pass the address of it. And then print these things again. And what you should see in this case, for example, is up here, it'll print 11 and 1999. Here it'll print 22 and 0. Alright, so that's the behavior after. So write your set function, write a main program like this, and do this a few times, right? Call set again, and haha.data should change from 22 to 44. Make yourself a few different variables, haha1, haha2, and set them up differently and call set on haha1, haha2, and then print out haha1 and haha2. And make sure, that nothing is stepping on anything and so on and so forth. So you should really, be exercising your code, be trying it out, throw a lot of different things at it, make it work. Convince yourself that this is good. Imagine you're at the store and you're trying to buy this set function, and somebody wants $30 for it. Well, you're not just gonna try it once and say, yeah, I guess that's worth 30 bucks. You're spending that kind of money on it. You really want to know that this function works in all possible cases. So imagine what kinds of things you would do to it, right? Kick the tires, push it up and down, make sure the suspension is good, check the oil. Really work these functions, okay? And then go ahead and do the automatic assessment. Now for this function, there's not that much to it. It's probably 2 lines of code to write your set function. But, as we develop longer functions, as you develop the functions for PA2 and as we go on to trees and stuff, right, you're really going to want to be in this habit of aggressively testing your code before you decide, okay, this is good, I'm ready to move on to my next function. So you can use these as practice for that kind of mindset. Alright, so what does our set function look like? It doesn't return anything. Well, in here, right, we're calling set with a pointer to a struct node, which means n is not a node. It's a pointer to a node. So we can dereference it by putting a star in front, but you're probably going to want to use that arrow notation. So inside here, if I were to take whatever argument name I use, I'm using n in this case, and say n arrow data, that's going to give me, this value. And if I say n arrow next, that's going to give me this value. And here's the cool thing, because we're using a pointer to a node, right, this up here actually says, take the number that's given to us, look at what's at that address. Well, the number that's given to us is the address of haha over here in main. So if I say, look at what's at that address, I am looking at this variable called haha, not a copy of it. I'm looking at the actual variable that main calls haha. And so if I were to look at this thing .data, I'm actually looking at this exact memory location. And so if I set that equal to, 22 in this case, when I come back to main, haha.data is going to be 22. So there's this idea of pass by value and pass by reference. And C is always pass by value. When we call a function, we always send it a copy of whatever arguments we're passing to it. So this n has the same value as the address of haha. But if I change n, I don't somehow change the address of haha, right? It's just a copy. But if I look at that copy as a pointer to memory, it points to the same thing as, what haha refers to. So we're kind of doing a pass by reference, even though we're always passing by value. And this is no different from what scanf does when you pass, ampersand I, so that scanf can change the value of I. That's the same mechanism we're using here. All right, questions about the ODP? All right, so on to PA2 then. So this is posted on Canvas. This is due a week from tomorrow, 8 a.m. Okay. I'm probably not going to give you an extension on this because we're starting this early enough. And particularly if you've done PA1, this does not take a lot of coding, right? It can take a while to conceptually understand how to do PA2 because it's sort of a fundamentally different approach to making a linked list. But in some ways, it's exactly the same thing as PA1, not just in behavior and main program, but even in the stuff that's happening inside our functions. It's definitely an analog to PA1. So once you kind of start to wrap your brain around dynamic memory and some of the mechanics of, dereferencing pointers and using these kinds of things and so on, once you sort of get that into your brain's muscle memory, if you will, PA2 becomes really quick, right? You can quite likely knock it out in a few hours, right? Once you're at that point. But as you work on developing PA2, right, you're going to probably run into various, hurdles, which are, manifestations of trying to understand dynamic memory and pointers, and allocating space and things like that. So it might take you a few days to do PA2, but I don't think it's going to take you a whole week. So probably no extension. So a week from Friday, 8 a.m., right? And that's our usual due date for assignments in this sequence. Yeah, just fork linked list 1 in Git. That's legit. All right, so let's go through some of the details of this, and this is going to look extremely familiar, right? You've seen this before. Linked list using dynamic memory. ODP 205 was the ODP we just talked about, and it's posted on Canvas. If you don't find it. All right, so our nodes are almost identical to what they were in PA1. It's still an integer field called data. It's still a next field, but the next field is now a genuine bona fide pointer to a struct node. And so there's no valid field. Again, the system's taking care of that for us. So simplified node structure with the same meaning as in PA1. All right. Required functions. So you need to implement an init function. Your init function looks different from PA1. It's the only function that changes. So your init function returns a pointer to a struct node instead of void. And the idea is you're going to, in your main program, declare a struct node star, call it sentinel or something. And to make your empty list, you're just going to say sentinel equals init. So let's do that a little more carefully. So here's our main program. You've declared, a struct node, probably in a .h file at this point. Maybe you typedef it. So let's say my list is called my list. So that's going to be the Sentinel. That's how I create my empty linked list. Just going to call my init function. Inside init, we're going to call malloc to create a node. We're going to set the next field equal to null. We can load the data field if we want to something recognizable. And then we're going to return the address of that node. And so up here, my list is going to get assigned to whatever that address was that we got from malloc inside init. And now my list refers to the Sentinel node of an empty list. Alright, that's the only fundamental change. Add looks exactly the same. We pass a pointer to a struct node and we pass a number. Now notice in PA1, this first argument was actually an array. Right? It was an array of struct nodes, but we declared it as a pointer to a struct node. Well, we're still declaring it as a pointer to a struct node. Arrays and pointers to memory are indistinguishable from each other when the program is actually running on the CPU. They look different in our C code, but when everything is compiled and linked and is finally executing, it's just a pointer to a variable of this type. Whether that's in an array or it's just, something hanging out in memory somewhere, there's no difference. Nothing gets passed to init. Uses malloc to find an empty space and make it a Sentinel. Exactly right. And so, as I said, that's the one function whose prototype is different from PA1. Alright, so what does add do? Make a new node, move down the list till you get to a node that's bigger than the number you're inserting. Put your new node right before that, so that your list is always sorted. Return 1 on success, return 0 in the unlikely event that you ran out of memory. If you ran out of memory, your system has probably crashed at this point. So, alright, print, again we pass a pointer to a struct node, move down the list, starting with the first node after the Sentinel, and just print out the data values one by one, single line, space in between. The nodes are always stored in sorted order, so when you print, your numbers will come out sorted as well. You don't have to do any extra work there. Delete, same thing, pass it a number, pass it a Sentinel node, right, the address of a Sentinel, and delete that number from the list. Again, you should only call this function if the number is contained in the list. So you can assume, if you like, as you're going through your list looking for the number to delete, you can assume that it's going to be in there somewhere. If you want to check to see if you run off the end, that's fine, but you're not allowed to print anything from these functions. And you don't return anything from this function because it's void. So in your main program, before you call delete, call search. See if the node's in the list. If it's not, print an error message from main. If the node is in the list, go ahead and call delete, and you don't have to worry about the return value. It's going to succeed. Oh, someone did try making PA1 run out of memory. Says it took them 5 to 7 minutes to test it. Cool. PA2, you're really not going to run out of memory unless something is catastrophically failing on your system. And if that's happening, the system's probably going to crash anyway. Alright, search, same thing. Go through your list, look for the number, return a 1 or a 0. So those are your main interface from your main program to your linked list. And I would say these are the only functions that your main program should have to call, other than, fgets and scanf and that kind of stuff. But for working with the list, your main program should not have to call malloc. It should not have to call free. It's really you know, doing these functions. So add should only print if not successful, and print should print the list. There shouldn't be anything else we print out. So no, you got the same messages being produced as in PA1, which I'll spec out down here in a moment. But don't print anything from these functions except the print function. The print function prints out the nodes, but never print anything else from any of these functions, right? If you run out of memory, don't print a message, return null. If you're out of memory and you can't add, don't print a message, just return 0. If you you know, are searching for something that's not found, just return a 0. If it's found, return a 1. Don't print anything, right? Even delete, right? If you check and you find that the number you're trying to delete isn't in there, you're not allowed to print anything. Okay, the only thing that prints is the print function, hence the name. But your main program will do all kinds of printing. Alright, so we'll talk about main next. So the same routines that we were using before, right? You got to work with the linked list, so start with the sentinel, move forward, follow the chain of nodes to do all of these things. If you want to insert, adjust the prior node to point to the new, adjust the new to point to what used to come after the prior, and so on and so forth. When you need a new node, call malloc. And the argument to malloc is size of struct node. And when you're done with a node, release it by calling free, where in this case PTR is the address of the node. Alright, main program. So the main program should never be doing things like, you know, sentinel.next equals sentinel.previous or something like that, right? The main program calls these functions to manipulate the list. These functions get down and you know, start at the sentinel and move forward and so on and so forth, right? But abstract data types, right? So our interface from the main program to the list is through these functions or other functions that you might write. Alright, program starts. It should create an empty linked list. That's just calling the init function. You can reuse main.c from PA1. You can probably reuse a lot of your code from PA1, and that's totally okay to do. Alright, run your program, print out a greater than followed by a space and wait for a command. User types in a command followed by enter, and it should be one of the following: I space number, P, S space number, D space number, or X. And this is exactly the same as what you had in PA1. If they say insert, you respond with either success, node already in list, or out of memory. If they say print, print the numbers on one line, spaces in between. If they say search, say found or not found. If they say delete, say success or node not found. If they say X, exit the program. Here's one other new detail. You have to free the lists from memory before you exit the program. And we'll talk about that too. But the behavior of main, same thing as in PA1. Alright, your deliverables are exactly the same as PA1. So all the above code is as described, a main program. Plenty of commenting. Okay, so I've highlighted some of the commenting that I want. So for each function, describe its behavior. I would also like you to provide a list of all the inputs, right? Tell me the purpose of each input, what type of variable it is. Tell me the meaning of the return value and what type of return value, if any. Right? And I'd suggest doing this in some kind of list, right? So, you know, this is my function add. Here's the arguments to it. There's an argument called list. There's an argument called number, right? List is a pointer to this, and it's the linked list. Number is an integer, and it's the value we're going to insert. The return value is, you know, an integer. 1 means this, 0 means this. Put that like right on top of the function, right? And it becomes documentation for your package. So this should be explained instead of comments immediately before the function. Additionally, your code should be commented throughout. Your main program should also be commented throughout the code. Now your main program is not called with any arguments, but if it was, you would want to do that also for your main program. Say, you know, how is this program run? Well, you can put 3 command line arguments, the number of sticks, you know, the highest number we can guess, etc., etc. Our main program doesn't take arguments, so you don't need to say, you know, what the inputs or outputs are. But you do need to comment your main program, right? The lines of that, the parsing and all of that stuff. And I still want that comment block in the beginning of the main program with the date, the assignment, synopsis in your own words, detailed synopsis please, and so on. And you're not allowed to say, you know, the details are found in such and such file in the Git repository. I mean, you can say that, but that doesn't take the place of having a comment block in here. And then make file for creating the executable image. Put this in a repo named linked list 2 on GitLab. Make sure I'm a reporter. All right, and I mentioned in Canvas 24-hour offer. So you have until noon on Friday to do the following. Make yourself a repo, add a README file to it, push it all over to GitLab, set me up as a reporter, send me an email, nmaciasclark.edu, right? Direct email to my Clark address, and ask me if I can see your repo. If you do that before noon Friday, that's tomorrow, I will go ahead and I'll try to pull it down and I'll tell you yes or no if that's accessible. And that takes the last piece of guesswork out of the whole submission process, right? That basically guarantees you that unless something changes, next Friday, 8 o'clock in the morning, I'll be able to download your repo. And then you just keep pushing things over there as you go, and you don't have to, you know, have a special thing to worry about with submitting the code. So that's a limited time offer. That's only until tomorrow morning, tomorrow at noon. All right, so grading, mostly the same as PA1. Some of the points are changed and there's some new aspects to this. So the kind of deal breakers are the same. If I can't download by Friday 8 a.m., 20-point deduction. I'll send you a note through Canvas and you have 24 hours. I'll try again Saturday morning. If I can't compile or it doesn't, you know, run, that's a 40-point deduction. If it's, you know, something other than PA2, if it's not, you know, building a linked list out of dynamic memory, that's a 0. And then partial points. So proper makefile, 5%. Everybody did a proper makefile. Just keep doing that, right? Strategically compile the pieces based on what's changed to build an executable image. So proper makefile, 5%. Your 5 main functions are now worth 10% each. So that's half your grade. Having working int, print, add, search, and delete. Main program is another 10%. Alright, I will run your program with Valgrind. And Valgrind should report no memory leaks, it should not give you any errors, it should not give any warnings. If it's a totally clean Valgrind run, you get 10 points. If I get 1 warning, you don't get the 10 points. Okay, so this is important. If you get any messages back from Valgrind, any warnings, anything like that, you have a bug in your code. Even if your program looks like it works perfectly, there's a bug somewhere. And you need to take care of that. Right? And this is going to be the case, you know, in any program that you write from here on out. Because pretty much all your programming, you know, down the road is probably going to involve allocating memory, building data structures. So you want to get into some Valgrind habits. No compiler warnings. So I'm going to compile on the Linux server with the default GCC command. It should not give any warnings. Obviously should not give any errors, because that's your 40-point deduction. But no warnings either. So if you get a warning, that's a problem. There's something in your code that's not quite right. Your program may look like it's doing the right thing, but there is a problem somewhere. So make sure you get rid of warnings. So that's 5%. Commenting before each function is 5. Comment block in the beginning of the code is 5. Comments throughout your code is 5. And then some sort of consistent indenting style is the last 5. All right. Any questions on logistics of PA2? Yes, ODP 205 is on Canvas. Well, you know, sometimes I put things on Canvas and Canvas doesn't take. But let's see. Dang. All right.
I just. Yeah.
Well, it should be there now. All right, so take a look again. It should be there. There's something I don't understand about Canvas because I did this morning and I switched to student view and it was there, and it's there in the A section also. Okay, so yeah. Thanks for letting me know. All right, so yeah, ODP 205 is available now. All right, other questions? So let me just mention something that's a little weird with linked lists. Can feel a little weird with linked lists. I think we talked about this some yesterday, but let's make a Sentinel. So I'm going to go loose and crazy with my C code here. So this is like pseudocode. So we've got a struct node defined, all of that stuff. We've got a Sentinel. We call malloc to get some space for it. So Sentinel is pointing to a node, right? And let's suppose we make a new node. And we call malloc. So now we've got, you know, this new box. And suppose we want Sentinel to point to new. So Sentinel is the address of this box. So we use this notation, Sentinel arrow next. So that means, you know, look at the thing that sent points to, that's this node. Look at the next field, that's this box down here. Let's set that equal to the address of this new node. So that creates this pointer. All right. Now imagine I do the following. I say new equals and I call malloc again. Malloc is going to set aside another chunk of memory. This assignment statement is going to change new to be right here. I'm using the same variable, new, to point to a different block of memory. New no longer refers to this block, but that block is still accessible because Sentinel's next field points to it. So if I wanted to put this, you know, right after the Sentinel, I could do something like this. New next equals Sentinel next. So Sentinel next says, you know, what's the address sitting right here? Well, it's the address of this block. This says take the next field of new and copy the value that's here to here. Well, the value that's here is the address of this block, so when I copy that, this block is pointing to that unnamed block. And then if I say sentinel next equals new, that says let's take the next field of sentinel and load the address of this block. I've got a list of 3 things pointing from one to the next. And now if I say new equals malloc, malloc finds another block of memory, and that's what new refers to. And this is what our system's going to look like while we're doing this code. We've got, 1, 2, 3, 4 blocks of memories. We've only got 2 variables. One of them refers to the block we just allocated. These 2 don't have any variables that are referring to them, but we can get to them, right? We can get to this node because this node is pointing to it, and we can get to this node because the sentinel is pointing to it, and we can get to the sentinel because we have a variable with its address in. So this is the precious, my precious, this is the thing that we need to keep, right? That's the handle to the list. That's how we get a hold of the whole list, is from the sentinel. Most of our data structures will have some kind of handle on them. And it's the one thing that we need to preserve and that we're going to use in order to get to the list. But as long as we've got this, we don't need variables. So we don't need to make a new variable name each time that we create a new node. We can keep reusing the same names. So yeah, let's talk about freeing memory. So we need to free any time that we call malloc. We're going to have a free at some point. But we can't free this list as soon as we malloc it, because as soon as we free a node, treat it as total garbage, right? If I free this node, make no assumptions about what's stored in the fields of this node anymore. Treat the node as completely unusable. So when you delete a node, right, after you've adjusted the pointers before and after it to skip over the node, then we can call free. And that's just like calling release node. But there's one other condition we need to be aware of, which is this exit command. This should exit the program after freeing all allocated memory. Because if this is my list, if I've done these things, by calling add and stuff, and my sentinel points to a node which points to another node, and then I exit my program, I've got to release those nodes from memory, otherwise I have a memory leak. So you're going to need to write one more function at least, which is going to be something like, release the list or something like that. And you're going to call that at the very end of your main program when you say X, and that's going to free all of these things from memory. And we'll go through the details of how to do that tomorrow, because I want to get through more of the core mechanics here today. But it's basically traversing the list and freeing the nodes behind you as you follow them. Let's see, do we need to track the number of all valid nodes? Nope, you do not. You could. I mean, sometimes it's nice to be able to know how big the list is, but there's no need to know that, right? And you can always find it by starting here and just following until you get to the end of the list. You could count, but there's no need for it. Does free change the values? I know it could, but does it? Meaning, if we know the memory address right after free, it might have the values intact. It depends on the system. I don't think that free on this system changes the values when you free memory. I think there may be versions of it that you can use, or switches that will overwrite them with junk. But pretty easy test program you could write probably. Allocate a chunk of memory, set some values, free it, and then try to access it. See if it's accessible and see what the values are in there. And that would be a fun exercise. All right, other questions? All right, let's look at some sample code. I have this error in set.c. Did you include standard.io.h? So that's where null gets its value from. So make sure you include standard.io.h. Cool. All right, let's look at some sample code. Yeah, we're not using myNull, we're using null for PA2. But if you were good and you used myNull everywhere in PA1, you can really just change myNull to null. All right, so here's our struct node, okay, and I want to develop something like a print function. And this is bogus code, okay? This is not code that you know mimics what you're going to do in PA2. What I'm doing here is I'm creating a linked list by hand with a sentinel and 2 nodes in it, right? So this was code from earlier in the week. So I've got my struct node. I declare 3 struct nodes: a sentinel, a first, and a last. And I'm setting it up like this. All right, it's just a little list we can play with. So just cobble that together by hand, right? Sentinel, set the data fields in those 3 nodes. Set next to be the address of first. Set first next to be the address of last, and last next is equal to null. And I'm doing this so I can practice with my print function. Now the print function is supposed to take the address of a node. Sentinel, I haven't declared it to be a pointer to a node. I've actually declared it to be a node. That's just to make my main program something that I can write without giving away, you know, too much of PA2. But I put a node in here, right? We really want Sentinel to be a pointer to a node. So when I call print, I'm going to call it with the address of Sentinel, right? In your main program, Sentinel is going to be a pointer already, so you're just going to say print Sentinel or search Sentinel or add Sentinel and so on. All right, so I'm going to, I'll call this sent. I'm going to call my print function. I'm going to call the argument sent for Sentinel, and let's just start off by just printing some stuff. So I'm going to print out the argument's data field and the argument's next field. And remember, I'm not saying sent dot data. That would work if Sentinel was a node, but since Sentinel is a pointer, I'm saying, okay, start with Sentinel, follow it to whatever it points to, that's what the arrow says, and then give me the data field of that. Or start with Sentinel, follow it to what it points to, and give me the next field of that. So here's a really simplified main program. It's just going to print the Sentinel's value. And when you're printing pointers, you can print them as integers, but if you print them as %p, you get like nicer values. It'll show you as a nice hexadecimal number. It'll be the right number of bits and so on and so forth. So let's use %p for printing the value of a pointer. And then if we run this, it tells us, well, our data is 42 and the next field is equal to this. So what is this? This number should be the address of the node called first. And if I run it again, you know, I get different values sometimes when I run it. Alright, so if I were to do the following, let's change Sentinel to be the thing that it points to, and let's print this out again. So now Sentinel was 42, pointed to this. When I change Sentinel to be what's at this address, now its data value is 10, and its next field is this. So I changed Sentinel to be, you know, this node over here. And if I do that again, change Sentinel to what it points to, and print out the values of the Sentinel object again, now I see my Sentinel, my 10, and my 20. And on this last one, you notice it says next equals nil. That's what null prints out as, right? That's a 0. And if I were to do this again, I'm going to get a seg fault. Because this last line that I did said set Sentinel equal to what it points to. Well, you know, after this third line, the next field is null, so Sentinel is now equal to null. And now I'm saying, find what's at address 0, give me the data field of that. Well, address 0 is not accessible, so I get a seg fault. So we don't usually write the same code multiple times. So we can throw this in a while loop. And we get the exact same behavior, including the seg fault, because we're going too far. So this while condition should be something different. So our Sentinel is here. We print the data in the next. We change Sentinel to be here. We print the data in the next. We change Sentinel to be here. We still want to print the data in the next. We're still okay. But then when we set Sentinel equal to Sentinel next, Sentinel equals null, that's when we want to stop. If we try to print the data field again, we're going to seg fault. So this can just be, well, sent is not equal to null. And there's a nice traversal. Alright, so we'll break this out more tomorrow. And I want to use this to look at how we can free the entire list from memory at the end of the program. So we'll work with that tomorrow. Go ahead and work on your ODP. Start coding 205 if you PA2 if you like, and bring questions to class. And we'll continue this tomorrow. All right, thanks. Have a good afternoon.